Characteristics of images. Before we proceed further to discuss about the sensors and their characteristics, we need to define and understand a few fundamental terms and concepts associated with remote sensing images. It is important to distinguish between the terms images and photographs in remote sensing. Then what is an image? An image refers to any pictorial representation regardless of the imaging media or wavelengths or remote sensing device that has been used to detect and record the electromagnetic energy. Image may be of two types. One is the photograph and another is digital image. Now, what is photograph? A photograph refers specifically to images that have been detected as well as recorded on photographic film. For example, the image shown in this slide is a black and white photo taken on a photographic film in the visible part of the spectrum. Photos are normally recorded over the wavelength range from 0.3 micrometer to 0.9 micrometer. This region is also known as photographic region. Based on these definitions, we can say that all photographs are images, but not all images are photographs. Therefore, unless we are talking specifically about an image recorded photographically, we use the term image. Images that are captured on digital media and represented digitally are called digital image. Photographs are also referred to as photographic images. Now, in case of digital image, as we have discussed already, digital images are detected and recorded on digital media, for example, charge coupled devices. And digital images are recorded and represented as an array of pixels. So, digital images are basically a two-dimensional matrix of pixels. Then what is a pixel? Pixel is the smallest two-dimensional non-divisible element of an image or of a digital image. Now, each pixel stores a value. This value is called digital number or brightness value, and this value is measured by the sensor, and pixel represents individual area scanned by the sensor. That means a pixel will represent a specific geographic area, and the specific geographic area, in other words, will be represented by a pixel. For example, if we look at this image and if we zoom a small portion from it, so it will look like this, and as you can see, this is basically an array of pixels or a two-dimensional matrix of pixels, and for each and every pixel we have a value, and this value basically controls how they appear on the computer monitor or screen, or how they will be on the paper while how they will appear on the paper once we take a printout. And this pixel is basically the smallest part of an image. We cannot subdivide a pixel further, and each pixel represents a specific geographic area. Now, a photograph could also be scanned and displayed in digital format by subdividing it into small and equal sized and square shaped areas called picture elements or pixels again, and representing the brightness for each area with a numeric value or digital number. Indeed, this is exactly what has been done in the photo that we have shown in this slide. Now, in fact, this figure is actually a digital image of the originally captured photograph. The photograph was scanned and subdivided into pixels, with each pixel assigned a digital number representing its relative brightness. The computer displays these digital values at as different brightness levels. Although photographs can be represented digitally by scanning it, digitally captured images and scanned photographs are not same. Electronic sensors actually electronically record the energy reflected, emitted or backscattered from the terrain. The value recorded by the sensor relates to the percent reflectance and forms the basis of object or material identification. Many digital image processing techniques rely on the digitally recorded pixel value. In a scanned photograph, the pixel value represents the reflected amount of light from the photograph and not from the original object, or not from the earth's surface rather. Thus, it differs from the originally captured digital image. And a digital image that has been captured on electronic media may also be represented photographically or pictorially by taking a printout. The two different ways of representing and displaying remote sensing data, either pictorially or digitally, are interchangeable in several instances. For example, if an image is being analyzed by means of visual interpretation, in this case both photographic and digital representations, regardless of how it was captured originally, may serve the purpose, because the analyst is interpreting the image visually and analysis is based on visual interpretation by human eyes. However, if the image is being analyzed in a digital environment, it must be recorded and stored on digital media. Another important issue that must be remembered is that although digitally captured images can be converted into photographic representation and vice versa, few details may be lost when converting back and forth. So, in summary, images may be recorded either photographically or digitally. They can also be converted back and forth to represent photographically recorded images in digital form, or digitally recorded image in photographic form. However, converted data cannot be used in many instances of image analysis. Orbital characteristics of remote sensing satellite. First, let us try to understand few definitions, and then we shall try to understand what the exact orbit that should be followed by a remote sensing satellite. Now, first is orbit. What is an orbit? Orbit is the path or the course of motion followed by a satellite in the space. So, this yellow line is basically the orbit. This is a virtual line that is followed by a satellite in the space, and it also has a ground trace. This ground trace is actually called path, and the time taken by a satellite to complete one circle around the earth is called the orbital period. For example, if the satellite starts from this particular location, then after completing the circle, it will come back at this place once again. So the time it takes to complete one circle is called the orbital period. Now, orbital plane. What is an orbital plane? Orbital plane is the plane in which a satellite moves. For example, here as you can see, we have this yellow shaded, this green shaded plane. This plane is orbital plane, or this maroon shaded plane, this is also one orbital plane. I mean, basically the plane on which the satellite rests is called the orbital plane, or the plane in which a satellite moves. Now this is the orbit and this is the orbital plane. Now satellite orbit may be classified based on the inclination. If the angle in between the equatorial plane and the orbital plane is 0 degree, then it is called equatorial orbit. So this is the equatorial orbit. Okay. So if the equatorial plane and the orbital plane creates an angle of 0 degree, then it is equatorial plane. Now if the orbital plane creates 90 degree angle with the equatorial plane, then it is called polar orbit, and in this case the satellite moves over the poles, and as you can see, this is the 90 degree angle. So this is called polar orbit, and the satellite may also have other angles in between 0 degree and 90 degree, and these are called inclined orbits. So this is the equatorial orbit, this is the polar orbit, and this is the inclined orbit. Now in case of remote sensing, the satellite should move over the poles. I mean, if the satellite moves over the poles and the earth also has a rotation from west to east, and these two perpendicular motions will ultimately enable the remote sensing satellite to capture the images for the entire earth, and that is why the remote sensing satellites are necessary to be placed near to the poles. I mean, the orbit may be exactly polar or maybe near polar if maintaining exact 90 degree is not possible with the equatorial plane. Next, the satellite orbits may also be classified based on their altitude. If the satellite is placed below of 2000 kilometer from the Earth's surface, then it is called low Earth orbit. And if the satellite is placed in between 2000 kilometer to less than 35,786 kilometer, then it is called medium Earth orbit. And if the satellite is placed at an altitude of 35,786 kilometer or above, then it is called high Earth orbit. Now remote sensing satellites are necessary to be placed very close to the Earth's surface, so that the sensors or the cameras can see the Earth clearly, or can see the Earth surface materials or Earth surface features clearly. That is why we need to place the satellites very close to the Earth, and essentially the satellites, remote sensing satellites, should have low Earth orbit, and generally they are placed within the range of say 400 to 700 kilometer or 900 kilometer or so. So this was about the altitude, and now Satellite orbits may be geosynchronous or geostationary. You might have heard about geostationary satellites. Now, geosynchronous, what does it mean by geosynchronous orbit? Now, if we place the satellite at an altitude of 35,786 kilometer, then the orbital period of the satellite is equal to the rotational period of the earth about its axis, that is almost 24 hours, and in this case it is called geosynchronous orbit. Geostationary orbit is a special type of geosynchronous orbit in which the shape of the orbit is almost circular and the inclination is 0 degree. I mean, orbital inclination is 0 degree, and in such cases the satellite appears stationary from a location on the earth's surface, or there will be no relative movement in between the satellite and the earth. And in the right hand side, as you can see, this is basically a geostationary orbit and this is a geosynchronous orbit. We have to understand that geostationary orbits are basically a type of a special type of geosynchronous orbit, and geostationary or geosynchronous orbits are generally used for meteorological satellites or for the telecommunications satellites or for the television broadcasting satellites, but remote sensing satellites are not placed on the geosynchronous orbit or geostationary orbit. Rather, we use a special type of orbit in case of remote sensing, that is called sun synchronous orbit. Now we have to understand that what does it mean by sun synchronous orbit. Now see, normally when we place a satellite in an orbit, then the connecting line in between sun and earth and the orbital plane, they create an angle in between them, and this angle is changing continuously. So the angle in between the orbital plane and the connecting line in between the sun and earth will change continuously. As you can see, here we have a 0 degree angle, here we have 90 degree angle. Okay, so the angle is changing continuously. But in case of remote sensing satellites, for each and every satellite we have a small rocket booster, and periodically these rocket boosters are ignited to rotate the orbit so that the angle in between the orbital plane and the sun earth connecting line maintains a constant value or constant angle. So as you can see here, the orbit is being rotated with the time, and because of the change in the season or in 365 days, this angle will remain constant. Then what is the benefit of doing this? The benefit is, if we maintain this constant angle, the benefit is the sun, the satellite will pass a specific location on the earth's surface every time at a constant local sun time. That means, for example, the satellite is passing over a specific geographic location at 10 a.m. local sun time is 10 a.m. Then every time it passes this location will maintain this constant time, constant local sun time. Then what will be the benefit of this constant local sun time? It will maintain at least similar illumination from the sun. I mean, incoming energy will be almost constant. But as you know, that it is not really constant throughout the year. I mean, during the March at 9 a.m., the amount of light we get is certainly different than the light we obtain in the month of December at 9 a.m. So the amount of light will be definitely different because of the change in angle in between the sun and the earth. But ultimately, we are trying to get similar illumination by maintaining the constant passing time. So in summary, in case of remote sensing satellite, we should have near polar orientation. Means the satellite should move over the poles, and the angle in between the equatorial plane and the orbital plane should be almost 90°. And then near circular, the orbit should be near circular, not I mean, it should have a circular shape, or it should not have the elliptical shape. But according to the Kepler's law, it has been said that orbit is an ellipse. Orbit cannot be a circle, rather it is an ellipse. But as much as possible, we should maintain a circular orbit, near circular. Why? Because to maintain the constant Earth and satellite distance, so that the view we obtain from the satellite remains of same quality. Then low Earth to ensure clear visibility of the Earth's surface, and sun synchronous to maintain a constant local sun time. And as you can see, the satellite, this satellite has a near polar orbit, and it is rotating over the earth, and the earth is moving from west to east, and as a result the satellite enables the scanning of the entire earth. And as you can see here, with slower motion, it is showing that the satellite is scanning a specific portion of the earth. Some portions may be left, for example, this portion is left, but ultimately this portion will be scanned after few passes. So this is basically the orbital characteristics of remote sensing satellites. Then the earth has the sun in one side. That means the sun will illuminate one side of the earth, and the satellite will move over the poles. In one side of the earth, it will move from north to south, and in the other side, it will move from south to north. If the satellite moves from north pole to south pole, then it is called descending pass. And if the satellite moves from the south pole to the north pole, then it is called ascending pass. Now the sun will illuminate one side of the earth, and that means one side of the earth will get the sunlight, and the other side will be in the shadowed area. Now which pass is in the sunlit portion of the earth, and which pass is in the darker side of the earth? Generally, descending pass is kept in the sunlit portion of the earth, and the ascending pass is kept in the shadowed portion of the earth. As a result, images, optical remote sensing images, are captured in the descending passes, not in case of ascending passes. Capturing the images in the ascending passes is not possible, rather images are captured in the descending passes.